Hello everyone. In continuation of our discussion on governance, I wish to introduce you another two terms today. One is called as effort and power. Maybe I can refer them as a governor effort and governor power. Okay, effort as such, you all know that effort means force. Okay, effort is a force and power is the rate of doing work, the rate of energy consumption, that is called as power. You all are very familiar. Okay, so what is meant by governor effort and governor power, that I would like to come back and discuss. Okay, before I go to there, so you all know what is meant by work. Work is basically, in very crude ways I can say that it is the product of force and displacement. Okay, if I apply force on a body and the body undergoes displacement, and what amount of force you apply multiplied by what is the displacement, that is called as work. And what is the energy? Energy is nothing but the capacity to do work is what is called as energy. Work and energy, they are equivalent to one another, or in other words they have same units. Then at what rate the work is done, per unit time, how much work is done, that is called as the power. Okay, so let me come back and introduce you what is called as the governor effort and governor power. That's what I would like to do. Okay, for a simple demonstration, I have represented, say this is the spindle axis and this is one position of the sleeve which is in an equilibrium position. So at this position of the sleeve, the governor balls and the governor spindle is rotating at an equilibrium speed, and that speed I call it as N1. Okay, everything is fine. The engine, so this is indirectly, this spindle is coupled to the engine. Okay, the engine is running at a constant speed and under constant load, and therefore this is also running at a constant speed, and that speed I am calling it as N. Okay, this is the sleeve, and this sleeve is in turn connected to the supply valve of the engine, and which will adjust the supply depending upon the load on the engine to maintain the constant speed. That is the function of the governor. That's what we have already seen it. Okay, let me come back and see, this is the sleeve which is in equilibrium position. Exactly, perfectly fine, no load change in the load. Okay, now let me imagine that the load on the engine has decreased. The load on the engine has decreased, therefore the speed will increase, and therefore the speed of this also will increase, and when the speed increases, the centrifugal force will increase, and that centrifugal force will make the sleeve to go up, and let me assume that, and it goes up and comes to this, and now the new equilibrium speed is N2. Now this is the new position of the sleeve, and this is the sleeve displacement. This sleeve displacement has adjusted the supply valve, and which will make the required supply to the engine to run at a constant speed. Okay, so this is the sleeve. When the speed changes from N1 to N2, the sleeve will move from here to here. Okay, we know that for any movement, for any displacement, okay, if at all I need to have some displacement, there must be some force acting on it. Okay, therefore when the sleeve starts its displacement at the starting point, there must be some force acting on the sleeve in the upward direction. Okay, and by the time it reaches this new equilibrium position, then again the sleeve stops there. Sleeve doesn't go up or down, and therefore there is no force acting on it. So I have some force on the sleeve at the beginning of the displacement, and by the time it completes its displacement, the force has vanished. So that means the force is not constant throughout the displacement, throughout the position, the displaced position of the sleeve, and it is varying. And therefore, what I shall assume that the force on the sleeve in the final position is 0. The force at the beginning of the displacement, when it is changing, I assume that force is maximum. So I have a maximum force here, and I have a 0 force here. So maximum force plus 0 force divided by 2, that I can call it as the average force. So therefore, now the governor effort, I am in a position to define the governor effort. What is governor effort? It is basically a force. Governor effort is a force. Where is that force? And what kind of force? It is the average force. Governor effort is the average force acting on the sleeve to move it from one equilibrium position to another equilibrium position. So therefore two positions is a must. Okay, whenever you are talking about the governor effort, governor sleeve position 1, sleeve position 2. If there is no change in sleeve position, there is no question of governor effort. So whenever there is change in the position, so from this position to this position, so what is the average force acting on the sleeve? That force is called as governor effort. Governor effort is the average force acting on the sleeve when the sleeve changes its equilibrium position from one to another one. This is what we call it as governor effort. I hope you all have understood. Okay, then what is power? Power is basically the rate of doing work, but probably here what we are calculating is the work. Okay, so what is the governor power? Governor power is nothing but the governor effort multiplied by the sleeve displacement. What is the sleeve displacement between the two positions? That is called as governor power. Okay, governor power is the product of effort, of course, governor effort multiplied by displacement. This is what we call it as governor power. I hope you all are clear. Okay, governor power. What is governor power? It is a product of governor effort and the displacement of the sleeve, that is called as governor power. Okay, all we have understood now. Now the next one is what calculation of this. How to calculate it? Calculations of the governor effort and governor power. I would like to do it. Okay, so before I jump to it, so please consider this case. Say, imagine that I have a pulley here. I have a pulley. Okay, then I have a inextensible string, or you can call it as belt. Okay, you have this thing on either side. Then I attach a pan here, and the weight of the pan what I have this side also is exactly the same. Okay, probably both of them are balanced. Now I have some weights here, known weights, say half kg, 1 kg, something like that, and here also I have something. Okay, here also I have, and the total weight whatever I have here, the total weight whatever I have here, both of them are equal. Therefore, the weight with which this side is being pulled, it is downwards in this direction, and the same amount of force that with that it is being pulled. And since both of them are equal, and none of them is going up or none of them is going down. Okay, it is in this position only and it is in this position only, though I have some weight which is acting in the downward direction. And this belt or the rope or thread that is being pulled, which is pulling that, this weight is being pulling it. And similarly the other way also, and both of them are balanced. Okay, fine. Now I take one extra weight, the stone like thing on which it is not written how many grams, how many kgs, nothing is written. Okay, I place it here, and you all agree that the weight, the force, this side is more, it will start going down. The moment I keep this will start going down, and this end will start going up. Okay, so imagine that now this is going down and this is going up. Okay, this is going down, this is going up because this side is more. Okay, now what I do is I take my hand and hold it. Okay, and hold it. What I do is I just hold it and I do not allow this to go up. I do not allow this to go up. Okay, then I have a question. What is the force what you have applied? What force you have applied to arrest the motion of this, to stop the motion of this? It is quite simple. Okay, it is, you take out whatever the stone you have placed now and go and weight. How much is the weight? So that is the force, okay, which is trying to pull it up or making it to go up, and the same amount of force you are applying in the downward direction, and therefore you are not allowing to go up. If your force is more than this, then it will start coming down. And your force is less than this, then it will start going up. It is not going up or it is not going down. That means whatever the force you have applied is the same as this. I hope you have understood. And this is the principle what we are going to use it now to calculate what is called as the governor effort and power. Very simple. Okay, so let me calculate for say Hartnell governor. Hartnell governor. Okay, this is the spindle axis. So let me assume that this sleeve is at one position and this is the sleeve is going to be in the second position. Now the speed is N1 and the speed is N2. And what is the spring force on the sleeve? Spring force and the mass of the weight, etc. And let me assume that it is S1 here. And let me assume that it is S2 here. Okay, and then let the speed N1 and then N1 I shall convert it into omega 1 and the radius of rotation is R1 and similarly here this is omega 2 and set is start. Okay, so these are the different positions, and what is the displacement between 1 and 2? This I call it as x1, 2. And apart from this, I also have what I call as A, B. Okay? And you suppose you may know or you may not know, I shall assume that obliquity effect is neglected. Okay? Obliquity effect, which is also called as gravitational weight due to the weight of the ball, that is neglected. Obliquity effect neglected. And whenever you neglect the obliquity effect, the C dimension, the dimension C has no significance. So whether it may be given in the problem or it may not be given, it doesn't matter. C value, I don't need it. What is C? C is the distance between the fulcrum of the bell crank lever from the axis of the spindle. Okay, that dimension which may be given or it may not be given. Okay, so now I shall write down for the position 1. Okay, so this is from here it is going to this position. Okay, so in the normal case, say, let me assume that it is running at equilibrium position 1. Let me assume that it is running at equilibrium position 1. So in that case, I can easily write it S1 multiplied by A is equal to MB omega 1 square R1 multiplied by B. This is neglecting the obliquity effect. You have only two forces all the time. Say force on the sleeve multiplied by the sleeve arm is equal to the centrifugal force multiplied by the ball arm. This is how it is the moment equation. Okay, so you know, say if you know the speed etc., you can easily find out from this equation what is the value of S1 you can find out. Okay, if at all you require. Okay, this is one equation. Okay, now the speed has changed to N2. Okay, if the speed has changed to N2 and the sleeve will occupy the new position, and again you have a similar equation S2 multiplied by A is equal to MB into omega 2 square R2 multiplied by B. But that's not, I'm not going to write like that. Okay, the sleeve is in this position. Please remember, the sleeve is in this position. Though the speed has moved, though the speed has increased to N2, how does it happen? How can it happen? I am applying some force, some extra force on the sleeve, though the speed has increased, I am not allowing it to go up. I am not allowing it to go up. And what force I have applied? Imagine that I have applied E max. The E max is the force, E, the effort what I have applied at the sleeve. What for? I don't want the sleeve to go up though its speed has increased. Okay, I have applied Emax. And what is the speed now? The speed is not N1, the speed is N2. The speed has become N2 and I have not allowed the sleeve to go up. The speed is N2. Okay, what is the spring force? It will remain as S1 because the spring force depends upon what is the compression of the spring. There is no further compression on either side and therefore it will remain S1. Speed is N2. This is S1. This is omega 2. This is R1, the radius has not moved because the sleeve has remained there only. But what force I have on the sleeve? So apart from this S1, I also have E max. Okay, the sleeve is going up. I don't want it to go up, therefore I am pulling it down. So I have a force E max in addition to S1. If I write down what is the equation, it is S1. The spring force which is acting in the downward direction. In addition, I also have what is called as E max. S1 plus E max divided by 2. This is the force on the sleeve multiplied by A is equal to mb. And what is the speed now? Please remember the speed is not omega 1, the speed is omega 2. Omega 2 square. What is the radius? It is R1. So what is the R length momentum? It is B. So S1 plus E max by 2 into A mb omega 2 square R1 into B. Okay, what all things you know? You know S1, you know A, you know mb, you know omega 2, you know R1, you know B, everything. And what is unknown? The unknown is E max. E max is so many newtons. This is the force. This is the maximum force. Please remember, when the sleeve really goes up, this is the force with which the sleeve will start moving up, and by the time it reaches the new position, the force becomes 0. So what will be the effort? If I denote it by E as the effort is equal to E max plus 0 divided by 2. Or in other words, E max by 2 is what is called as the effort of the governor. And if I want to calculate what is the power, so E multiplied by x12, E multiplied by x12, that will be the power of the governor. So this is how you can calculate, and little later I am going to take one problem appeared in the university examination, and that this calculation I am going to demonstrate. And before I go to the Porter-Governor calculation, which is quite simple, okay, so before I do that, so I just want to tell sometimes they give only one position and they don't give what is the second position, speed or anything, and they just calculate what is the effort and power. So in that case, the second speed, you imagine that it is 1% more than the present speed, or 1% less than the present speed. So therefore, many times effort we define it as the average force acting on the sleeve to change the sleeve from one position to another position when 1% change in speed has taken place. Okay, for many times it is 1%. Sometimes they give you what is the displacement, what is the speed change, etc. In that case, you don't have to take out that 1%. I hope it's clear. Okay, so now before I take up a numerical problem, then how to calculate Porter-Governor effort and power calculation for Porter-Governor. Okay, Porter-Governor. Again, I would like to make it simple. So I assume that Lu is equal to LL. I assume that Lu is equal to LL and CRU is equal to CRL. Sorry, RCU. This is RCU. Radius of the collar at the upper end, radius of the collar at the lower end. So this is what the Porter-Governor I have here. So therefore I know that it is alpha is equal to beta. alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, alpha minimum is equal to beta minimum, etc. Okay, so with this, let me, for this kind of thing, I would like to calculate. Maybe the governor is like this. This is where I have a sleeve. Okay, this is length is equal to this length say this is alpha and say this is beta, and if I take this and this distance is what I am calling it as the height of the governor, and similarly what is this? This also is h, because alpha is equal to beta. So this is Lu cos alpha, this is L cos beta, alpha is equal to beta, Lu is equal to Lf, and therefore this is also h and this is also h. Okay, let me make use of the expression in general. Omega square is equal to G by h. What is our expression? Mb plus ms by 2 into 1 plus k. Since alpha is equal to beta all the time, so k is equal to 1 and the whole thing divided by mb. I am going to further simplify this. So ms by 2, 1 plus 1, okay, therefore 1 plus 1 by 2. So I shall make this mb plus ms upon mb. Okay, this is what is equal to omega square. Okay, now I shall so I can write down the expression omega 1 square is equal to G by h into mb plus ms, or I shall take G inside. It is 1 into mb G plus ms into G divided by mb. So I have taken G inside, which will be very soon known to you. Okay, now when the governor sleeve is in this position, say now this is the expression, the speed is omega 1. Okay, now the speed has changed to omega 2. When the speed changes to omega 2 and assuming that omega 2 is more than omega 1, the sleeve is going to occupy the new position in the upward direction. Okay, so now I shall call position 2. The speed now has become omega 2 radians per second. Please remember, I am not allowing the sleeve to go up. I am pulling it down by applying a force Emax. So in this, though the speed has changed, the speed is omega 2. And what is the h? H will remain same. And okay, mb. And therefore now I can write down what is the speed now. I have applied some extra force on the sleeve. Though the speed has changed, I have not allowed the sleeve to go up. Therefore, now it is omega 2 square. This is equal to 1 by h into mb into g plus what is the force on the sleeve now? It is ms into g plus Emax. I have applied an extra force on the sleeve and not allowed. So this is divided by mb. Okay, so now you can simplify this and find out what is Emax. This is Emax. Okay, so then this is equal to Emax over Newton, and therefore to find out what is the governor effort. Governor effort is equal to Emax divided by 2. This is over Newtons. Okay, so now I would like to calculate what is called as power. I would like to calculate what is governor power. What is governor power? Governor effort multiplied by sleeve displacement. Okay, so now to calculate sleeve displacement, I just keep this Emax expression. Emax I know already. Now what is the sleeve displacement when the sleeve moves from one position corresponding to omega 1 to another position corresponding to the speed omega 2. Okay, for that I shall make use of the expression h is equal to g upon omega square mb omega square mb plus ms divided by mb. The same thing, instead of omega square was here, I have taken it. To H I can find out. So corresponding to position 1, let me call this as position 1. I shall find out what is H1. H1 is equal to G upon omega 1 square into MB plus MS divided by MB. Similarly, I would like to find out for the second position when the speed has become omega 2 and the sleeve has really moved to the new position. That time it is G upon omega 2 square MB plus MS divided by MB. Omega 2 square. Okay, this is corresponding to the first position. This is corresponding to when the sleeve has moved here. Then, what is H1? I can find out easily H1 minus H2. I can easily find out this. So, this is nothing but say G into MB plus MS divided by MB. Okay, into bracket 1 upon omega 1 square minus 1 upon omega 2 square. Okay, you find out H1 minus H2. Okay, this sleeve displacement is equal to 2 times H1 minus H2. This is the sleeve displacement, and sleeve displacement, once you know, then the governor effort multiplied by sleeve displacement, that will give you what is the value of governor power. I hope it's clear. Now we shall go through the problem which you already have. You are having the problem and I shall read it along with you, and before that I shall make the space to solve the problem. Okay, I shall read it along with you. Please read it loudly along with me. They rate the radius of rotation of the balls of a Hartnell governor is 100 mm. At the minimum speed of 300 rpm. Okay, when the speed minimum 300 rpm, that time the radius is 100 mm and therefore the radius is also minimum. I can write down along with you the data. So R minimum is equal to 100 mm, and we have what is called as L minimum is 300 rpm. And make use of this and find out what is called as omega minimum. So many radians per second. I wish you to calculate. Okay, neglecting gravity effect. That means obliquity effect is neglected. You have only two forces in the moment. Spring force multiplied by A is equal to centrifugal force multiplied by B. Determine the speed. Okay, what is asked? Okay, determine the speed after the sleeve has lifted by 50 mm. Okay, so let me call this is minimum, and then I have another one. So I will be asked what is omega 1. Let me assume that the sleeve has moved to position 1 from the minimum. That time, what is the speed? When the sleeve displacement x minimum to 1. X minimum to 1, this is given as 50 mm. The sleeve has moved from minimum position to the new position, that is 50 mm. So also determine the initial compression. So what is normally, when the sleeve is at its lowest position, what is the compression of the spring? That is called as initial compression. So I shall denote it by delta initial. So this is equal to S minimum divided by K. So how much is this? It's quite simple. Delta initial is equal to S minimum divided by K. Okay, this is also asked. You are also asked to governor effort. Okay, what is the governor effort? And you are also asked to calculate what is the governor power. Governor power is how much? Okay, so from minimum position to position 1, when the sleeve moves, what is the governor effort and what is the governor power? Okay, take length of the ball arm as 150, so B is equal to 150 mm. and length of the sleeve arm is equal to 100 mm. Then weight of each hole MB into G, and this is equal to 40 Newton. And from this I want you to calculate what is MB, so many kg. This 40 divided by G is so many kgs. And the stiffness of the spring, in addition to this you also have one more information, that is stiffness of the spring K is given. This is 25 Newton per millimeter. This information is given to you, and okay, it's quite simple, and I wish you to read the problem once again if required. Okay, so now once you are ready, the first analysis for minimum position of sleeve and equilibrium speed. The sleeve is in its minimum position and rotating and staying at an equilibrium position. Okay, so now, I don't know whether you require the diagram, etc. Probably you can draw that, and I am going to write down. Just check. So I have to neglect the obliquity effect. I have only two forces. One is S minimum divided by 2 multiplied by A. S minimum by 2 into A is equal to the centrifugal force, that is MB, into omega minimum square R minimum multiplied by B. Check what all things you know. S minimum you don't know, A is known, MB is known, omega minimum is known, R minimum is known, B is known, and therefore, of course, with the proper substitution, with the proper units, all that, when you calculate it, yes, minimum you get so many newtons. And immediately you can calculate what is called as delta minimum, the initial compression of the spring. This is equal to S minimum divided by K. Okay, S minimum is in Newton and K is Newton per millimeter. In that case, this is so many millimeter. If this is Newton and this is in Newton per meter, in that case it may be meter. So it may be millimeter or it may be meter. Be careful and then accordingly express it. It may be millimeter or it may be meter, depending upon the units. Okay, this is the first part. Okay. Now the second one. So now it has assumed that it has moved to the second position. So what is the displacement? The displacement is what is called as x minimum to the new position 1. Then when the sleeve has moved from one position to another position, the sleeve arm and that displacement, they form a triangle. The initial position of the sleeve arm, then the new position of the sleeve arm, and in between the two you have a triangle. And that is nothing but x minimum to 1 divided by A is equal to, so R1, the new position, minus R minimum divided by B. You know x minimum to 1, this A is known, R minimum is known, B is known, and from this you can easily find out what is the value of R1. So this may be in millimeter or this may be meter, depending upon what units you substitute. So you know the value of R1. Okay. So what is asked? We are supposed to calculate what is the governor effort. So first I would like to calculate what is the governor effort. The sleeve is at its lowest position. The sleeve is at its lowest position. But the speed has changed to omega 1. The speed is from omega minimum, it has increased. Then you may ask, when the speed has increased, why the governor sleeve is still in the minimum position? I have applied some extra force on it, E max, and not allowing it to go up. So therefore, that time what is the moment equation? S minimum plus E max, the whole thing divided by 2. S minimum plus E max divided by 2. This is the force acting on the sleeve. Sleeve is in the lowest position, but the speed is omega 1 into A. E is equal to, so the centrifugal force mb. What is the speed? Speed is not omega minimum, it is omega 1 mb omega 1 square, and the sleeve has remained in the lowest position, therefore the radius is r minimum, and this multiplied by b. So what all things you know? S minimum you already know, E max is unknown, A is known, mb is known, omega 1 is known. Omega 1, do we know omega 1? Sorry, I'll tell you how to calculate omega 1. So omega 1 is not known, okay, R minimum and B. Okay, so I shall proceed to this, okay, after finding out what is omega 1. After finding omega 1. Okay, let me assume that the sleeve has moved to the new position omega 1. So new position omega 1, it has really moved. So S1 is equal to S minimum plus K multiplied by X minimum to one position. So I know K, I know X minimum to one position, I know S minimum, therefore S1 I can find out. Of course, you have to be very careful about the units. So S1 is known. So in the new position, new equilibrium position, S1 by 2 multiplied by A. S1 is known already. This is equal to mb omega 1 square R1, okay, multiplied by B. What all things I know? S1 I know, I have found out. Then A is known, mb is known, omega 1 is unknown. What is R1? R1 is known. I have found out R1. R1 is known. B is known. What is unknown? The only unknown is omega 1. So many radians per second. First we calculate omega 1 square, then take square root, and then find out what is omega 1. And omega 1 is known. That omega 1 you substitute here. Come back here. S minimum is known. E max is unknown. A is known. mb is known. Omega 1 is known. R minimum is known. B is known. So therefore the only unknown, and that is E max, you find out, that is so many newtons. Then from this E max you find out E. What is E? E max divided by 2. E is nothing but the governor effort, that is so many newtons that you find out. So once you know the governor effort, then how to calculate governor power? Governor effort multiplied by the sleeve displacement, which is already given to you. X minimum to 1 is 50 millimeter. So governor effort E multiplied by the sleeve displacement, that will give you the governor power. I only have demonstrated the procedure. I wish you to do it and gain the confidence, and in that process, if you get any doubt, please let me know. I shall be very happy to clear it. Thank you. Good day.